We are working on section 4.6, which is exponential growth and decay models. So this equation is going to be y equals y naught e to the k times t. This will be our growth or decay equation. Y naught is the initial amount or population. So t is time. Y is the amount or population at time t. And k is the relative rate of growth or decay. So kind of depending on what you guys are looking at, this equation will be growth equation of k is positive, it's a decay equation of k is negative, and everything in this section revolves around this formula. So we're just going to be working with this formula over and over again. So first of all, they're going to look at this in kind of little finance type. So let's say we want to find how long it takes for $2,000 to grow to $7,000 at 7% compounded continuously. So the equation is A equals P e to the RT, which if we compare that to Y equals Y naught e to the KT, we see that this is actually a exponential growth equation. A and Y are kind of the same, P and Y naught are the same, Rx is K, and everything else is identical. So we're saying, all right, the amount we're trying to grow to is 7,000. The initial investment's 2,000. Our rate is 0.07 times t. So I would divide the 2,000 across, and I'd get 7 halves is e to the 0.07 t. To undo exponential base e, I apply natural log to both sides. That's the logarithm base e that cancels. And then I'm left with 0.7 t on that side, so I just divide the 0.7 across. Sorry, 0.07 across. And this will tell me how long that takes. So natural log of 7 halves divided by 0.07. This is exact form. This is 17.897 years. Okay, so that is our first one. We just use the equation and solve it for the variable. So second example we're going to look at is what if we have the equation y equals y naught e to the kt. And let's say they tell us y naught is 80, t is 3, and y is 50. And we want to find k. And we want to answer in terms of natural log. So what that means is we're going to leave the k in its exact form, basically. So, okay, y naught is 80. So I'm going to replace y naught with 80. We have e to the k times 3. And y itself is 50. So I need to get the e by itself, so I divide the 80 across. 50 divided by 80 is 5/8. That equals e to the k times 3. We could say 3k either way. K times 3 and 3 times k are the same. We apply natural log to both sides because we need to get rid of the exponential base e. And so we're left with natural log of 5/8 equals 3k. So we divide the 3 across. And natural log of 5/8, all that divided by 3 is our k value. This is k in terms of natural log, so the problem said, hey, leave it in terms of natural log. So that's all you guys do. That's it. If it said it wanted it to a decimal, then we type it into a calculator. Okay, so that one's not too bad. Let's look at the next. Alright, so we got some radioactive substance, which I'm going to use Ra for radioactive in this section. So radioactive substance decays according to the equation A of T, so this is going to be the amount still radioactive, equals 300 e to the negative 0.00012 times T. And we want to find the amount still radioactive at, or I guess we'd say after 2 years. Then we want to know what about after 6 years. And then part C a little bit different, we want to find the half-life. So these parts A and B are pretty easy. If we want to find the amount still radioactive after 2 years, we just plug 2 in for the T here in this equation. So we just get 300 e to the negative 0.00012 times 2. And then we want to get the one for 6 years. It's 300 e to the negative 0.00012 times 6. So we'll just type those into our calculator and we'll see kind of what we get. So 300 e to the power of negative 0.00012 times 2. That is 299.928. And they didn't give us units. Let's just suppose that this was 300. Let's just say this was grams. So if this was 300 grams, then this would be that many grams as well. If this was like kilograms, then that would be kilograms. If this was pounds, it would be pounds. But so we're just going to suppose that was grams. So we have units along with these. So let's see, what about if we wanted the 6 years times 6? So just same equation, but put a 6 there. And we get 299.784 grams is still radioactive after 6 years. Okay, so that's differs a little bit. That means that probably this thing's decaying pretty slowly, so you have to probably look at a pretty sizable time before you start seeing the amount actually start to decay at a decent rate. Because, start with 300, and here, this is almost 300, and this is, again, almost 300. So 2 years to 6 years isn't really, not that much is happening. So we want to find the half-life, which is, well, how long does it take for our initial, say, 300 grams? How long does it take for that to decay down where half is still radioactive? So what we do is we go to our equation here. So half-life is the time it takes for the initial amount to decay, where half is still radioactive. All right, so what we want to do is half of 300 is 150. So we're going to replace the amount still radioactive with 150. And we're going to figure this out for how long, what's the time, this time would be in years. How many years does that take for that to occur? So I divide the 300 across. This gives me a half equals e to the negative 0.00012t. Since after 2 years and after 6 years we were seeing the decay be very little, I'm expecting the half-life to be pretty big. I think it's going to take a pretty long time for the 300 grams to decay down to 150, because over 6 years the 300 grams decayed only to 299.784, so it barely decayed over 6 years. So this is probably going to be a pretty big number. So we apply natural log to both sides. And then we get natural log of a half. We divide the negative 0.00012 across. And this will tell me how many years that takes. So I'm going to type that in my calculator. So we get 1/2 divided by negative 0.00012. So this takes about 5,776.227 years to decay, where the initial amount, half, is still radioactive. So this is our half-life. And so like we said, after 6 years it barely decayed. It makes sense that if you want half of it to decay, it's going to take a pretty long time for that to occur. Alright, so you guys will see one kind of similar to that in your homework. Next, we got a little carbon dating type problem thing. So they tell us... Oh, wait, no, sorry. This is just going to be another half-life deal. So they tell us 20 grams of something radioactive is present initially. And then they tell us 6 years later, 10 grams remains radioactive. And so they ask us how much is radioactive after 12 years. Okay, so we have 20 grams. So 20 grams over 6 years decayed to half of its amount. So what that means is this has a half-life. Whatever this stuff is, this has a half-life of 6 years. Because from the information the problem gave me, the initial amount of 20 grams decayed down to half of its amount, 10 grams, over a 6-year period. So after 12 years, it's going to undergo a half-life decay again. So of the 10 grams that are still radioactive, another 6 years pass, and half of those 10 grams are radioactive. So our answer is 5 grams. Basically, it undergoes a decay of 2 half-lives. So the initial amount, 20, gets cut in half over the first 6 years to 10 grams. Then over the second 6 years, the 10 grams gets cut in half again to 5 grams. And that's it. All right, so now we're going to look at a carbon dating problem. So for carbon dating, we get this equation, y equals y naught e to the negative 0.0001216t. And carbon dating only works on stuff that was once alive, and basically it kind of pinpoints the time of death of the object. So like what happens is, as long as something's alive, there's a certain fixed ratio of carbon-14 to carbon-12 in the atmosphere. And so what happens is whenever the thing dies, the radioactive carbon-14 undergoes radioactive decay, and based on how far that's decayed down from the normal atmospheric ratio that you see, you can tell how old the thing is. So here's our carbon dating equation, and let's say an old arrow, so made out of wood. So we're going to just kind of figure out how old is the tree that the arrow was made out of. So let's say an old arrow has 22% of the normal ratio of carbon-14 to carbon-12. And we want to know how old is it. So this one we've got to be a little, is going to be a little weird. What we do is we say, okay, this has decayed down to 22% of the initial amount. Why not? That's the initial normal atmospheric value you see. So I'm going to set y equal to 22% of y naught. And the way I'm going to do that is I'm going to do 0.22 times y naught. That's 22% of y naught. That equals y naught e to the negative 0.0001216 times t. Now what happens next is we want to solve this for t. The y naughts, you guys can divide by y naught, and they'll cancel out on both sides of the equation. So we get 0.22 equals e to the negative 0.0001216t. We apply natural log to both sides of the equation. It cancels the e. And so I get natural log of 0.22 equals negative 0.0001216t. To get the t by itself, I divide the negative 0.0001216. That will be t. This is sort of exact form, but I want to figure out what is this amount actually. And you can't be with carbon dating, you can't be so precise that like you know the exact day and the exact times. You kind of just gives you kind of ballpark stuff. So this is 12.451 years approximately. I guess actually 2. We'll round. It's 0.7, so it should round up to 2. This is about how many years ago that arrow is dated back to. So that's basically how you use it. You see what ratio has the thing decayed down to, replace y with that ratio times y naught, and then you just solve it out and you get your solution. Okay, last problem. This will be kind of similar to your last one on your homework. They have this disease spread thing, and they say, here's an equation, or they give us kind of an equation. This is a little bit different than the one in your homework, but in this equation, f of t is the number of people susceptible to a disease, which means, I guess, they're able to catch the disease. Time is in days. And they give us a couple questions. So they say, how many are susceptible initially? And then they want to know how many after 9 days. Okay, susceptible initially means time is 0. So if you put 0 in for t, you get e to the 0, which is 0. Or sorry, e to the 0 is 1. So you just get the 2,000 back. Or you guys could use, hey, this is an exponential equation. The number, the y naught number that's sitting in front of the e, if we go all the way back up and look at our initial equation, this y naught number is the initial amount or the initial population. So that 2,000 that was sitting there in front of the e, that's going to be our initial amount just due to the fact this is an exponential growth formula. And that's the number that's sitting in front of e. So you say, well, how about how many are susceptible after 9 days? We just want f of 9, which is going to just be 2,000 e to the negative 0.07 times 9. And then we just type that in, and they want you to round to the nearest number, so you don't have like, 0.7 of a person or something like that. So they want you to, like I get 1060.18, so 1065.18. Don't do this. This is not good. We need to round to the nearest. Person. So we'll say round to nearest person. When you guys deal with population models where you're dealing with organisms and stuff, or just things that are alive, this is a pretty common deal where you round to the nearest animal or the nearest person or the nearest whatever. All right, so that should wrap up 4.6. We'll stop there.